All right, hey everyone, welcome back for linear algebra. This is going to be our fourth lecture, and we'll be starting section 2.2. So 2.2 is pretty long, which means we're going to break it up into two videos, and we'll just have to, take them one step at a time. So today, this first video, we'll talk about Gaussian elimination and how we can, just our first technique for solving a linear system of equations. So let's just get right into it. The goal for today's class will be to just simply reduce a linear system to an equivalent system that can be easily solved with back substitution. So we'll take, this is a follow-up to what we did last time, which was sort of an introduction to what is a linear system and how do we solve it. And today we're going to solve several. Okay, great. So given some linear system, and here we have one written down, 2x plus y minus z equals 3, x plus 5z equals 1, and negative x plus 3y minus 2z equals 0. Given that system, we're going to introduce two matrices that go along with it. So there's the coefficient matrix, which we'll just call the matrix A, and it looks like this. Just take the coefficients. Okay, so 2, 1, negative 1, 1, 0, 5, and negative 1, 3, negative 2. This will be our coefficient matrix, okay? And the reason that we give it a name is just so that we can reference the matrix of the coefficients of a linear system, right? This is not to be confused with the augmented matrix, which we saw last time. The augmented matrix looks like, okay, we put brackets A and then a vertical bar and then a column vector B, where B is the vector of constants for the linear system. So 3, 1, 0 in this case. So the augmented matrix, A augmented with B, looks like this. We start off the same. 2, 1, negative 1 going down the columns, 1, 0, 3, negative 1, 5, negative 2, augmented with 3, 1, 0. Just like this. Okay, and these two matrices are gonna, we're gonna learn some operations to do on matrices that will then allow us to take a linear system, convert it into a matrix, do some operations, and then eventually solve the system. Okay, but we have to start by introducing some terminology. Speaking of terminology, last time we saw an example where we had a 3x3 system of a system of 3 equations with 3 variables, and when we did some mysterious operations, we were able to convert that thing into, we were able to convert the augmented matrix into a matrix that looked kind of like a triangle, right? With like zeros on the bottom and like non-zeros on the top of the triangle, a right triangle, I mean. Okay, that lent itself very nicely to back substitution, but unfortunately not every linear system will have an augmented matrix that when you do this reduction, you end up in a triangle, a perfect triangle. However, there will be a staircase pattern that will emerge. Something like this, okay? And I don't know what this is, staircase. And interestingly enough, a matrix in this staircase form, it's called row echelon form. I'll give you the definition in just a moment. But the word echelon comes from the same Latin root as, well, I guess the word for stairs. If you look up stairs in like Spanish or French or something like that, you'll find that they use the word, like in French, the word is échelle, something like that. Okay, and it represents this pattern living inside of the matrix. So, okay, let me tell you now what row echelon form for a matrix is. So a matrix is considered to be in row echelon form if, number one, all zero rows, all zero rows. That is, all rows which are made of just a string of zeros are at the bottom. And the leftmost in every single not okay, and two in each non-zero column okay sorry in each non-zero row the first non-zero entry is to the left of every first non-zero entry. Let me tell you what before I tell you where the non-zero entries live, let me give you a name for this non-zero entry. We're going to call this called the leading term, a leading entry. Is to the left of every leading entry okay in a row below it. Okay. Right. So in other words, so let me give you an example because what is that definition? That's not very helpful. So let me give you an example, right? Let's look at this one. 1, 4, 5, 0, 1, 2, 0, 0, 7. This thing is in row echelon form because look, first of all, there's no zero rows, but if there were any, they would be at the bottom. Then let's go to the first non-zero entry in any row. Let me just circle them. I'll highlight them. Okay, there's a set. There they are. Right, it's the first non-zero entry in each row. So you just proceed from left to right until you find something that's not zero. And then you just ask, if you look vertically, let's take, for example, this one, right? That one, if you look at any row below it, the leading entries that come below it are on the right of that number. So it lies to the left of every leading entry below it. That might be even easier to see in the first example, right? This first one is to the left of the other two because the other two are leading entries in rows that are below that first one, okay? Let's look at another example. Something like this. 1, 1, 2, 3, 0, 5, 8, 13, 0, 0, 0, 0. This one has a row of all zeros. You could have even done something like, 0, 0, 5, 8. This is a little bit more representative of an example. Okay, so we don't have a staircase pattern, but these leading entries, each one is to the left of all the leading entries below it, and uh, there's a row of zeros, but the row of zeros happens at the bottom, right? And so, well, let me highlight them just like the other one. Okay, good. Other examples. I think this is good. Let's do a larger example, something like this. Because after all, matrices could be just super large. So 1, 0, 1, 1, 2, 0, 0, 2, 2, 7, 0, 0, 0, 1, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Perfectly good matrix, and it's in row echelon form because every leading entry is to the left of all the leading entries below it, right? This is the pattern, and this is what it means to be in row echelon form. So our goal will be to transform matrices to get into row echelon form. Okay. By the way, as an exercise, you may want to watch the rest of this video first. Try pretending that each of these matrices is an augmented matrix for some linear system, and then try to solve that system. And let me do it just for the first one because it's going to be very straightforward. So the first one, if it were a linear system, pretending that it's augmented looks like this. Just pretend that there's a vertical line there. It looks like 1x plus 4y equals 5, 1y equals 2, and 0, like 0x plus 0y equals 7. For what x values are all three of these equations true statements in mathematics? For x values and y values? None. This is inconsistent. Okay. The other two, if you try it, you're going to get too many solutions. And so, but we'll talk about that. We'll talk about the notion of a free variable at the end of this video. And so maybe we'll finish watching the video before trying the other two, or just go for it. I mean, hey. Okay, anyway. This inconsistent means no solution. We mentioned that in the last video. Okay, so but like, I'm sure you're wondering, how do we get into row echelon form, right? It's one thing to know what row echelon form is. By the way, row echelon form, the reason that we want it is because it will make it very easy to do back substitution, and we'll talk about that as well. But to get into row echelon form, we have to do something. We have to apply what are called elementary row operations. So an elementary row operation is going to be an operation that you can perform to the rows of a matrix, which will transform the corresponding, it'll change the linear system of equations that corresponds to that matrix, but it will change it in such a way that it remains an equivalent system. Okay, and we did actually talk about this last time, where you like add something to both sides of one of the equations, but you use the fact that it was a statement about equality from one of the other equations in your linear system, right? Instead of going the linear equation route, we're just going to talk about them as like operations that you can do to the rows of a matrix. So let's try it. So the first one is pretty straightforward. We can interchange two rows. Okay. Obviously, switching the order of two equations in a linear system is not going to change the solution set at all. Yeah, if you have a solution to both equations, I don't care what order you put the equations in. Yeah, and so interchanging two rows of the matrix is totally allowed. I also want to give you some shorthand because otherwise you have to use, right, what we're building are the tools to construct a logical argument for why two linear systems or two coefficient matrices or something are equivalent. And yeah, unless you're prepared to write a sentence for every row operation that you use, we may want to use some shorthand. So interchange two rows, we do like this. Ri, and then a double arrow, and then Rj. So row I, what this means is switch row I with row j. And in a matrix, it'll look like this. 1, 1, 2, 3. So what we'll do is we'll have a sideways arrow, a new matrix, 2, 3, 1, 1. And then we label the arrow, because it was an operation, we label that arrow with what the operation was. So it would be R1 interchange with R2. Row 1 interchange with row 2. Okay. Wasn't so bad. Second row operation that you can do, you can scale an entire row. We simply label that one with just like k times r, like that. Or k times ri, I guess. So what this means is multiply all entries in row I by some number k. By the way, implicit in that is you can also divide like all the elements in a row by some number. Like if I wanted to double all the entries in a row, if I wanted to cut in half all of the entries in a row, I could just multiply by 1/2 rather than divide, or I could divide by 2, right? This is multiplication. Okay, so let's do an example. So we'll just keep the same example. 1, 1, 2, 3. We have an arrow because we're doing an operation. And it will be 2, 2, 2, 3. If I wanted to, for example, scale row 1 by 2. So this would be like 2R1, like that. Okay, this third one is simultaneously the most common and most annoying to denote. Let me write it for you. You can add or subtract, because multiply by -1, a multiple of one row to another. The shorthand for this one is going to be whatever row you're adding to, so Ri, plus the number that you multiply the other row by, row j. So if I want, example, 1, 1, 2, 3. Say I want to add -2 copies of row 1 to row 2. Let me write the shorthand first. So I'm going to do row 2 plus -2 row 1. You can also put, and I'm gonna do it, row 2 minus 2 row 1. After all, that's just plus -2 row 1. And when I do that, so I take row 1, multiply by -2, that would give me the row -2, -2, and then I add that to the second row. So the first row doesn't change. The second row, 2 minus 2 is 0, 3 minus 2 is 1. By the way, we just got this matrix into row echelon form in one step. It's kind of nice. Great. Okay. So okay. I do want to just give one other definition. It's not really a definition, but the idea is at some point, what we have to do is called pivoting, and we're going to create pivots. So we want to when converting a matrix into row echelon form, we need to choose where the leading entries will go. Okay, that choice that we make, so it's a choice, right? Because I could have just switched the first two rows. And now suddenly the first leading entry, instead of being 1 1, could have been a 2 3, and then I do something to the second row so that there's a 0 underneath, and whatever the next entry is, whatever this guy became, instead of being a 1, it would be some other number. And that, okay, whatever that number is, it's obviously different from 1. And so I've made a choice, but I've still arrived at a matrix which is in row echelon form. So because of that difference, right, this is like choosing whether you want to solve a logarithmic equation using laws of exponents or laws of logarithms, right? I mean, the end result will get you the same. When solving a linear system, the end result will be the same solution set. However, the path that we take to get there could be totally different, right? So this is called pivoting. Pivoting. It's when it's when we choose where the leading entry will go. And by the way, this is called pivoting, and the chosen entry is called the pivot. It's called the pivot. So you might hear me say something like pivot around the 1 or something. Pivot around, yeah, okay, good. Good. Okay. So now, each of those elementary row operations as a standalone might not be enough to get a matrix into row echelon form. However, row reduction is simply the process by which we reduce a matrix to row echelon form using a sequence of elementary row operations. In other words, we just manipulate this matrix over and over until we get something which is in row echelon form. So we're going to do it for this one. And it's going to be, notice I've saved myself a lot of space. So this tends to consume a lot of space on your notebook. I encourage you to persevere and, if possible, try to write neatly throughout the whole process. It's bizarre, but you'd be amazed at how awful it is to get all the way to the end of a problem and then figure it out because you weren't writing neatly, your rows got messed up, and so you miscopied a row at some point. Okay, not worth. And we've all been there. Okay, it'll happen. It'll happen. Okay, so remember, to apply a row operation, we draw an arrow and a new matrix. For the sake of everyone's sanity, I will not be doing this one row operation at a time. Usually the process is to do one column at a time, and I'll tell you what that means in a second. But yeah, so we'll do several operations all at once. Okay, but we're given this matrix. It is a 4 by 5 matrix, 4 rows and 5 columns. Okay, and we're gonna put this thing in row echelon form. And by the way, this isn't corresponding to some linear system. They just handed us a matrix and they said, put it in row echelon form, or row reduce this matrix. We're just going to do it. Now, the very first step is to pivot around this 1, and generally speaking, that's always the first step. We just want to put a non-zero entry in the top right corner, top left corner, okay? Because we can't do any better than that. If the leading entries in each row have to be as far to the left as possible, then we might as well start at the top left corner. That entry will be as far to the left as possible, and it will be to the left of every leading entry below it, right? So we just, okay. Well, if we want that to be leading entry, then it should have all zeros below it, just like in our little staircase picture. Yeah, zeros below it. Okay, so to do that, what we need to do is, I'm going to give myself a little bit more space. We are going to add multiples of the first row to all of the other rows. The easiest one to see is the bottom one. If I just add row 1 to row 4, then row 4 will in particular, row 4 will have a 0 in the first entry. So let me write that. Row 1 plus 1 row 4. Then, to get zeros in the other two leftmost entries in the other two rows, we're going to have to do -2 row 1. Oh, sorry. I wrote this backwards. Row 4 plus 1 row 1. This is we have to stay consistent with our shorthand. Otherwise, this is going to get very confusing. So row 4 plus 1 row 1. Then we'll take row 3 plus -2. I'm going to put -2 row 1. And row 2 -2 row 1. The reason is, look, there's a 1 in the top corner. If I add that entire row to the bottom row, this -1 will cancel with the +1 and become a 0. Okay, so let's do that. Let's do these one at a time. Row 4 plus row 1. Apparently it's going to row 4 because we wrote row 4 first, right? That's very important. Okay, when we do this, we have -1 plus 1 is 0. We have 1, so like negative. I'm just adding these entries together. Yeah. So 1 plus 2 is 3. Oh. 3 plus -4 is -1. 6 plus -4 is 2. And 5 plus 5 is 10. Let's go again. So this time we're going to add this entry plus -2 copies of the first entry, and then this one plus -2 of these. Yeah? Let me erase that guy. Okay. So 2 minus 2 is 0. 3 plus -4. Oh my goodness. My hand keeps touching the scroll button. Let me do this. There we go. 3 plus -4 is -1. 2 plus 8, +8, is 10. 1 plus 8 is 9. And 5 plus -10 is -5. Okay? And then we do the same. So that was this one. Now we'll do the last one, which is that, 2 plus -2 is 0. 4 plus -4 is 0. 0 plus 8 is 8. 0 plus 8 is 8. And 2 plus -10 is -8. The first row does not change, so we just copy it. 1, 2, -4, -4, 5. And you have now done the first step. Notice, this is like solving a Rubik's Cube. You have to get the first side done, and then you do some algorithms for the next side and the next side. This is very similar, okay? Very similar principle. So now we need, okay, so the next step is we're going to have to get a non-zero entry over here. Non-zero because notice there are non-zero entries in that column aside from the 2, which means that we'll have to pivot at some point in that column. But we can't pivot around to 0 because that's not, okay, this is silly. 0 is not a non-zero number. Okay, follow that under sentences I thought I would never say. Great. My suggestion, simply interchange these 2 rows because one of them has a non-zero entry in the second column. Okay, when we do that, so our shorthand will be that row 2 gets interchanged with row 3. By the way, if you're wondering, oh, do I have to show all of this, all of these row operations with the shorthand and stuff like that? Yes, file that under showing your work. And if it's missing, you will get the problem wrong because we can't just, first of all, without it, it just looks like a bunch of matrices on the page. And so we have no idea what you did. But also, part of this subject is constructing rigorous mathematical logic or using rigorous mathematical logic in order to arrive at a solution. And so without any justification, there's no logic. This is just a bunch of matrices. So it's 100%, that's like the point. It would be better to show the row operations and not the matrices, except good luck. Okay, you need both. You kind of need both. All right, the first row doesn't change. 1, 2, -4, -4, 5. The second row and the third row switch, so I'll just write them in that order. 0, -1, 10, 9, -5, then 0, 0, 8, 8, -8, and then 0, 3, -1, 2, 10. That bottom row didn't change either. Okay, and what's awesome is that, notice we have a leading entry here, and this is almost a leading entry. It's just that we need to get rid of that bottom non-zero entry. But we can do that just by adding 3 copies of the first row to the third row. That gives us a very clear next step. So that would be that row 4 gets a copy of 3 row 2. Right? If you add 3 copies of row 2 to row 4, we'll end up with a 0 in that second entry. So again, 1, 2, -4, -4, 5 stays the same. 0, -1, 10, 9, -5. When we add 3 copies of the first row to the second row, the next row also stays the same. Row 3 has nothing to do with this as well. So 0, 0, 8, 8, -8. And now when we add 3 copies of the second row to the fourth row, 0 plus 0 is 0. -3 plus 3 is 0. 30 minus 1 is 29. 27 plus 2 is also 29. And -15 plus 10 is -5. Okay, great. Now, notice the next candidate. So we've got leading entries going down the diagonal. Now we have another column with another non-zero entry that occurs after in the row directly after the row with our most recent leading entry, which means we're going to have to pivot around this 8. However, I don't fancy multiplying row 4 by 8 29ths. Wait. Yeah, okay. You see the problem. 29 eighths of row 3. I mean, it won't really matter, but in the interest of using our second row operation, I think we should just scale row 3 by 1/8. Okay, that's going to be very quick. We just do 1/8 row 3. It's going to make this matrix much easier to look at. So 1, 2, minus 4, 5, 0, -1, 10, 9, -5, 0, 0. When we scale by 1/8, 1, 1, -1. That's nice to look at. And then 0, 0, 29, oops, 29, 29, -5. Okay. And now we have one last operation, which is if we just take -29 row 3 and add it to row 4. Okay, so row 4 plus, minus 29 row 3. That's crazy. But our final matrix is, again, the first two rows are going to stay the same. So 1, 2, -4, 5, 0, -1, 10, 9, -5, 0, 0, 1, 1, -1. Look, I have to be careful. Got to make sure that my columns look like columns. Otherwise, there's no tell. This is how it happens. Okay, you just have like slanted columns and then you're doomed. Okay, and then the last row, when we take -29 copies of row 3 and add them to row 4, notice both of the 29s are gone. And what survives is like a positive 24, right? Because -29 times -1 is positive 29, plus -5 is positive 24. Oh, okay. Arithmetic, by the way, don't use your calculators for these. Just if you have to, practice your addition tables, because you're going to sit here for 2 hours row reducing a 5 by 5 matrix if you have to use your calculator. Yeah, it is what it is. By the way, notice this is in row echelon form. Let me go ahead and highlight all the leading entries. 1, -1, 1, and 24. It's in row echelon form, even though there's that double zero, because every leading entry is to the left of all of the leading entries below it. Okay, good. Wow, I left myself 2 pages and only needed 1. That was nice. I do have some comments. So number 1, row echelon form is not unique. If you don't believe me, just do one more operation where you scale the last row by 1/24. You'll have a 1 in that bottom. Let me just show you. One more. Let's just do one more operation. 1/24, row 4. What does this become? 1, 2, -4, -4, 5, 0, -1, 10, 9, -5, 0, 0, 1, 1, -1, 0, 0, 0, 0, 1. Now that is a different matrix. It differs by 1 number. I probably should have copy pasted it in hindsight. But notice it's still in row echelon form. Go and imagine highlighting the leading entries. They make a staircase. So yeah, this is in row echelon form, but it's a different matrix. And we could have gotten it by the same from the same matrix that we started with, right? So row echelon form is not necessarily unique. Okay. Also, again, notice that we had to move from left to right and from top to bottom. That was exactly the algorithm. We started in the first column and worked down that column. Then we moved to the next column, then worked down that column, and so on. You kind of just zoom into the bottom right corner, essentially. And there is one other comment that I would like to make, which is that elementary row operations are reversible. And I challenge you to try undoing all of the row operations that we just did on that matrix to recover the original one. You should be able to. Row operations are reversible. In fact, that gives rise to the next definition, which is what happens, like how do you know if two matrices are equivalent? We call two matrices row equivalent. So it's a very specific notion of equivalence, but we call them row equivalent if there is a sequence of elementary row operations taking you from one to the other. So if we call them A and B, you can do row operations to A until you get to B. But if you can do row operations from A and get to B, then you just do the inverse of those to B. That's a bunch of elementary row operations that you're doing to B, and it'll take you back to A. So, yeah, and so that's what it means for those matrices to be row equivalent. But now I have a theorem which is better than definition. Well, okay, it's not better than the definition. It's just as nice as the definition. Says that two matrices A and B are row equivalent if and only if they can be reduced to the same row echelon form. I want to prove this for you, but this is going to be a little bit loose of a proof. So first, we're going to say, okay, so this is the reason I want to show you this proof is because it's an if and only if proof. So it has two parts. And if and remember from I think our first video, an if and only if statement is a statement about two mathematical statements which mutually imply one another. In other words, so what we're saying is, what this theorem is saying is that two matrices are row equivalent implies the fact that they can be reduced to the same row echelon form. But two matrices can be reduced to the statement of the fact that two matrices can be reduced to the same row echelon form implies that they are row equivalent. In other words, there's a sequence of row operations taking one to the other. Okay, so we're going to prove this in both directions. The way that these proofs go is you assume one of the statements, and then you use it to prove the other one. And then you do the other way. You assume the second statement and use it to prove the first one. So we're going to assume that two matrices are row equivalent. In other words, there's a sequence of operations that takes you, of elementary row operations, that takes you from A to B. And I'm just going to call it E, elementary. Sequence, this little symbol E is the entire thing that we just did, reducing that matrix. Okay. There is some sequence of elementary row operations that takes A to B. Okay, now take B to row echelon form. And I'm going to call this capital R sub B. It's a matrix which is in row echelon form, and I guess we'll just use F for a sequence of row operations that takes you from B to its row echelon form, or to this row echelon form. Okay, let me produce for you a sequence of row operations that takes you from A to this row echelon form. E, F, do E and then do F. Go from A to B and then go from B to RB. There you go. In other words, A and B can be reduced to the same row echelon form, namely RB. Okay, yeah. Okay, good. Again, this is why I call it quote unquote proof. I would have to say all of that precisely in order to call it a proof. And the book actually does. So I recommend reading that section alongside this explanation. Okay, if you can call it an explanation. So now we'll go the other way. So this one says, suppose that you can reduce A and B to the same row echelon form, which we'll just call R. Suppose that, and we'll just call it EA and EB. For there's a sequence of elementary row operations that you do to A to get down to R. And there's a sequence of elementary row operations that you do to B to get down to R. Okay? Apparently, A and B should be row equivalent. There should be a sequence of elementary row operations that you can do to A to get to B, or do to B to get to A. But remember that elementary row operations are reversible. I can get from R to B by doing EB like inverse. Just undo all the row operations that you did to B to get to R. Just do them in the reverse order and reverse operations, right? But notice if I interchange two rows, undoing that is just interchanging two rows. That's an elementary row operation. Or if I tripled all of the entries in a row in one single row, that's an elementary row operation. But to undo that, I would have to divide all of those entries by 3. But dividing by 3 is the same as multiplying by 1/3. Scaling a row by 1/3, though, is an elementary row operation, right? Adding multiples of one row to another row, to undo that, you just subtract multiples of one row from the other row, right? And so, great. So EB inverse is how you get from R to B. But if you go from A, if you just string this sequence of row operations and then this one together, you get row operations that look like this: EA, EB inverse. That's a sequence of row operations that gets you from A to B. That's it. In other words, A and B are row equivalent. Okay, what are these diagrams? This is just a tool for explanation for the proof. Okay, the proof is spelled out with more precise language in the book. However, there's no diagrams, so that's not very helpful. Okay, great. So the last thing that we have to talk about is Gaussian elimination. And Gaussian elimination, by the way, is going to feel like, wait, how is that different from row reducing a matrix? It's just Gaussian elimination is every time that you use it, you have a context of a linear system. So it's row reduction, but applied to a linear system, and we're hunting for solutions. Okay, good. So Gaussian elimination is the process by which we solve systems of linear equations. Step 1, write the augmented matrix for your linear system. Get right on it. Okay, here we go. 0, 2, 3, 8, 2, 3, 1, 5, 1, minus 1, minus 1, minus 5. Step 2, row reduce this matrix. Okay, here we go. Is there a way that the book likes to do this one? I don't know. Yeah, I don't think so. Okay, well, I guess the book wants to interchange these two rows first. We'll do it. We'll trust the book. So let's go. Row 1, interchange with row 3. This will give you 1, minus 1, minus 1, minus 5, 2, 3, 1, 5, 0, 2, 3, 8. Now, if you're thinking, why didn't I interchange the second row and the first row? You absolutely can. However, I always like to put, if given the opportunity, I always like to put a 1 in the top corner, because the next step, if there was a 0 and we had to interchange something to get a 1 into the top corner, then the next step is going to be to clear out that column. And it's a lot easier to add multiples of a 1 to every column, to every row, than it is to add multiples of, like, for example, a 2. And so, yeah, having 1s as the leading entries is generally more desirable. And actually, pretty soon we're going to find that it's actually essential. So, yeah. So this is a more, if you're going to interchange two rows anyway, you might as well put the 1 up in the top corner rather than the 2. Okay, now we add -2 copies of row 1 to row 2. So row 2 minus 2 row 1. This will give you an, okay, 1 minus 1 minus 1 minus 5, 0, because negative 2 plus 2 is 0. If we add positive 2 to 3, we get 5. If we add positive 2 to 1, we get 3. And if we add 10 to 5, we get 15. 0, 3, 5, 15. Now I'm second guessing my second entry here. Oh, wait. Mostly, oh, aha, I have copied the original matrix wrong. If you look at the bottom row, this must have been bothering you, those of you who were watching me for step 1. Okay, if you look at the bottom row, notice the coefficients are negative 1, or positive 1, negative 1, negative 2, and negative 5. Yeah, that'll get you every time. But again, I said this before, and I'll probably keep mentioning it as we go. Computational errors are bound to happen, and so at every step, be suspicious of that step. As this is actually a point that is not talked about enough in these videos, which is that when, like, oftentimes you'll watch a pre-recorded video and there are no errors in it because you don't want to see any errors. But like, errors are an integral part of mathematics, and you will be making many errors. Okay, you're not the only one. This is like normal. Okay, so negative 2 goes through. There we go. Now we're adding negative 2 copies of row 1 to row 2, and when you do that, negative 2 times negative 2 is positive 4, plus 1 is 5. And I had worked this out earlier on scratch paper, and I seemed to remember having a row of multiples of 5. And even if not, I was suspicious that, like, wait, there's a 5 here and a 15 here. I kind of want to scale that row down by 5. But then I would have a fraction, and I try to avoid those, at least on principle. Okay. So, yeah, so anyway, something to be careful of. Anyway, that suggests the very next natural step, which is to scale the next row down by 1/5. So 1/5 row 2 gives us the matrix 1 minus 1 minus 2 minus 5, 0, 1, 1, 3, 0, 2, 3, 8. Now we can pivot around this 1, the second one. So add negative 2 copies of row 1, of row 2 to row 3. So row 3 minus 2, row 2. And that gives us 1 minus 1 minus 2 minus 5, 0, 1, 1, 3, 0. Okay, 0. Negative 2 plus 3 is 1. And negative 6 plus 8 is 2. This whole time, we should be writing an augmented matrix. So I'm going to put the vertical bar. Apparently, I have a bad habit of not doing that. But think about the context of the problem. This is actually an augmented matrix. The matrix to the left of the vertical bar is the coefficient matrix, and the column vector to the right is the column of constants for the linear system. So we do want to distinguish between them. That's going to help for the third step of Gaussian elimination. So the first step was to write the augmented matrix for your linear system, which I forgot a vertical bar for. The second step is to row reduce that matrix into row echelon form. And the reason I started talking about augmented matrices is because, look, we're done. In fact, we have ones on the main diagonal, which is kind of great. Step 3 is to solve the resulting linear system. But the resulting linear system is an equivalent linear system. That's the point of all of this row echelon form stuff, is that we're about to write down a new linear system, which is equivalent to the original one. And so it's going to have the same solution set. So let's do that. Equivalent linear system. It'll be the system x1 minus x2 minus 2x3 equals -5. x2 plus x3 equals 3. And x3 equals 2. Well, x3 equals 2. Great. Which means that this row reads x2 plus 2 equals 3. So x3 equals 2. If x2 plus 2 equals 3, then x2 better be equal to 1. But if x2 and x1, if we know x2 and x3, we can solve for x1. Apparently -5 is x1 minus 1 minus 2, or x1 minus 3. But what number do you subtract 3 from in order to get to -5? It better be -2. Two x3. I did it again. Whoa. This number right here. Twice now. I think it's because this subscript matches the coefficient. Two times the same error in one video. That's not good. Okay, it happens. Okay, so -2 times x3. Be careful. That's -2 times 2 is -4, and x2 is 1. So -x2 is -1, and -1 minus 4 is -5. So x1 minus 5 is equal to -5. x1 must be equal to 0. Again, really helps to question yourself at every step. Okay, good. Notice this is the unique solution. Our hands are tied. It's not like we can have more than one solution here. And so what we do is we just write our solution. So solution set. x1, x2, x3, like this, equals 0, 1, 2. And this is just this notation with column vectors is the best way of representing our solutions. Okay, x1 is 0, x2 is 1, x3 is 2. Good. Okay, one more example. This one's gonna highlight different things. So the row reduction is going to be relatively simple for this one, but let's still represent it as a linear system, as an augmented matrix. Okay, be careful when transcribing the coefficients. Apparently, there's room for error there as well. We've got the first row is 1, minus 1, minus 1, positive 2, augmented, and then positive 1. 2, minus 2, minus 1, 3, 3, minus 1, 1, minus 1, 0, minus 3. Okay. We already have a non-zero entry in the top left corner. So now we're down to the next part. Step 2 for Gaussian elimination is to row reduce. So might as well pivot around this top leftmost 1. And so we'll add -2 copies of row 1 to row 2, and just 1 copy of row 1 to row 3. So row 2 minus 2 row 1, and row 3 plus row 1. The first row remains unchanged. 1 minus 1 minus 1, 2, 1. The second row, when you add negative 2 copies of the first row to it, you have a 0. Then negative 2 times negative 1 is 2 plus 2, or minus 2 is 0. 2 minus 1 is 1. Negative 4 plus 3 is minus 1. And negative 2 plus 3 is 1. Double check that one for sure. Okay, good. Next, we just add the first row to the last row. So 1 plus 1 minus 1 is 0. Minus 1 plus 1 is also 0. Minus 1 plus minus 1 is minus 2. 2 plus 0 is 2. And 1 plus negative 3 is negative 2. Look at this grid of zeros that shows up in the bottom left corner. If we're going to pivot, we're going to have to pivot around this 1 now, right? How are we going to get a non-zero entry over here? Can't do it, right? Not without compromising this guy. And so, yeah, we pivot around the 1 in the first 1 in the second row, which means we have to clear out all the zeros below it, or all of the, we have to clear out the space below that 1 and turn it into a bunch of zeros. When we do that, watch what happens. So to do that, right, we add 2 copies of row 2 to row 3. So row 3 plus 2 row 2. And when we do that, we have negative 1. Sorry, wow, the first entry stays the same. So 1 minus 1 minus 1, 2, 1. 0, 0, 1 minus 1, 1. And then 0, 0, because, you're adding that row, you're adding row 2 to row 3. Oh, 2 row 2 to row 3. Okay, when we add 2 to negative 2, we get 0. When we add negative 2 to 2, we get 0. And when we add 2 to negative 2, we get 0. In other words, row 3 was just a copy, a scalar multiple of row 2. That's interesting. So our final, this matrix is in row echelon form. Look at that. All the rows of zeros are at the bottom, and all of the leading entries are to the left of the leading entries below them. Is what it is. What is this as a, okay, so this augmented matrix is apparently an equivalent linear system to the one that we started with. Let's write it as a linear system using the x1, x2, x3, x4. It reads like this: x1 minus x2 minus x3 plus 2x4 equals 1, and x3 minus x4 equals 1. Interesting. Okay, so we now need a definition in order to finish the job here. We're not quite done. This is a new linear system. We have to solve it with back substitution, but how do you deal with this, right? This is a very strange thing to even try to back substitute, because the variables aren't taking on just numbers. So we call a leading variable. A leading variable is a variable corresponding to a leading entry. Corresponding to a leading entry. Let me circle them for you. x1 and x3, leading variables. Okay. Every other variable is a free variable. It's called a free variable. Every other variable is a free variable. Free variable. So how do we report these? Well, what we do is we just solve for the leading variables in terms of the free variables, like this. Oh, didn't leave myself enough space. Well, it's not so bad, fortunately. We just do the following. First of all, x3 equals x4 plus 1. I'll put 1 plus x4. Okay, I just added x4 to both sides of this last equation. Notice the free variables are x2 and x4. So x4 in particular is just x4. Is what it is. It's a free variable. X2 is also a free variable because it's not a leading variable. So it just is what it is. And x1 can be obtained by substituting our expression for x3 and subtracting everything to the other side of the equation. So x1 is 1 plus x2 plus x3, also known as 1 plus x4, and then minus 2x4, which I'll go and write as 1 plus x2 minus, 2 plus x2. Combine like terms, of course, right? Algebra style. 2 plus x2 minus x4. And then we're left with we're left with the task of submitting our final answer. So remember, our final answer is reported like this. We give a column vector of x1, x2, x3, and x4. And for any of these, how do we make any one entry that's in the solution set? Well, it has to be of the form sum vector 2, 0, 1, 0. I'll explain where this came from in a moment. Plus x2 times 1, 1, 0, 0. Plus, let me give myself a little bit more space, x4 times negative 1, 0, 1, 1. This is the solution set. And in this solution set, we are assuming that x2 and x4, they're free variables. They can take on any value. So any vector that you can write as a sum of this form where x2 and x4 are real numbers, that is a viable solution to this linear system. And I encourage you to try plugging in some numbers for x2 and x4, adding the corresponding vectors together, and then checking to see if that thing is a solution to all of the equations in the original linear system. It's not obvious, but it is, and you should check it if you don't believe me. You should check it anyway. Okay, good. I pulled the wool over your eyes. How did I get these vectors extracted? Secretly, what I did was I knew that there would be a vector of constants It's the numbers that are showing up on the right-hand side of the equal sign. Notice we've solved for x1, x2, x3, and x4 in terms of numbers and free variables, right? Free variables are going to help us span the solution set. We haven't talked about what the word span means, but you know, right? It's a way of almost parameterizing elements inside of the solution set. If you have been reading, there is a good amount of discussion on this in chapter 1 that we didn't, in section 2.1, sorry. So the content of the last video that we didn't discuss explicitly. If you've been reading along in the textbook, this should not come as a surprise to you. And if not, then you double need to check them to make sure that vectors of this form are solutions to the linear equation, and check like 2 or 3, okay? I also recommend reading in the textbook. I mentioned before, but I'll continue to bring it up, that these videos are meant to supplement the textbook itself. Okay, good. So anyway, what I did was I extracted the constant numbers on the right-hand side of the equal signs. So there was a 2, and there was a 1, and there were zeros, like, you know, whatever. Then I looked at the coefficients in front of x2, and in the first 2 equations, there was a coefficient of 1, although it looks like I've written them as zeros. There was a coefficient of 1 in front of the x2s, and like, you know, zeros in front of the x2 terms of the last 2 equations. That's where I'm getting this vector 1, 1, 0, 0. And the last one, if you look, there's a -1, a +1, and a +1 in front of the x4 terms in these last equations. And so here we have the entire solution set parameterized by, we had 2 free variables. In other words, there's a 2-dimensional family of solutions here. If you're looking for the geometric interpretation of like what's going on here, this is the intersection of 3 3-dimensional planes in 4-dimensional space, 2 of which were dependent on the other, one of which was dependent on the other 2. And so the intersection set was a 2-dimensional plane. And we've actually just written down its vector equation. So this is a very, if you like the geometric, I'm not going to try and draw that because, you know, 4-dimensional space. But there's a very geometric story going on as well, wrapped up inside of all of this algorithm, right? Okay, a definition and a theorem to end on. So this business with number of free variables and whatever, number of free variables isn't always a constant for or like we said, the row echelon form is not unique, right? However, the explicit solution is unique, right? The solution that we wrote down, that's the unique solution, and you would have gotten that solution no matter what row echelon form that you had used. It depends on a certain number of free variables. And the number of free variables depends on the number of rows in the matrix and the number of leading entries, or the number of leading variables, right? So we defined this rank. So the one thing that will be constant, so the row echelon form is not constant. It's not unique. However, the one thing that is unique about this system is the number of non-zero rows. Like, you won't be able to find 2 row echelon forms of the same matrix, one of which has a row of zeros when the other one doesn't. And so it makes sense to define that number, at least, and by the way, it will show up as the single most important number that you find, that we talk about in this class. We will come back to this. Okay, but it's called the rank of a matrix. The rank of a matrix is just the number of non-zero rows in its row echelon form, among other things. There's a lot of properties that this number satisfies, like a lot. It's a very important number. Oh, and we denote it with just like rank parentheses A. Okay, and we have a theorem about it. The theorem is what I was saying, which is that we can compute the number of free variables. Number of free variables. So if A is the coefficient matrix for a system of linear equations in n variables, as long as that system is consistent, then the number of free variables is precisely n, the the total number of variables, minus the number of non-zero rows in the system. Each non-zero row contains a leading variable, and all of the other variables are free variables. And so that's what this formula is reflecting. Okay? Good. Okay, so that's all for this video. That is not all for section 2.2. So the next video is going to talk about Gauss-Jordan elimination, which is different from Gaussian elimination. It'll be another strategy where we essentially take row reduction even further than we did with just Gaussian elimination. Do more row reduction and less back substitution. It's a question of like, how far do you solve the problem? So we'll talk about that next time. And I will see you then.